Okay, today is the last session before the final exam. We're gonna solve a few examples to recap what we did in during the term. Actually, I will solve you a few problem. Oops, sorry. Yes. Here is the first problem. Let's remember the torsion. What we have. Yes. Okay, we have a cantilever member. This point is A, this point is B, C. On this member, we have an axial force, which is P. And also we have one more torsion moment at the end of the member. And the length of the member AB is 1 meter. And then this portion is 0.6 meter. Okay. Here is this is the section, and this portion is okay. We have a solid section for the AB section of AB is a solid section with a diameter of 10 centimeters, and BC is here. This is the section BC, and the diameter is here 8 centimeter, and this is a hollow section, pipe section. Here is the section, the mid portion is a gap, so this thickness is 1 centimeter. 1 centimeter. And all the other given data in the question is sigma allowable is, yes, tau allowable is 900. E, elastic modulus, yes. Okay, the question is, we have 3 questions for this sketch. The first one is, I'm gonna write the full text here. This was an exam question. Perform stress check on A, B, and CB when P is 0, P equals 0, and MT equals 0.25 Ton meter. Okay, this is the A, and the next question here is B. If rotation of and C is, let's say it's theta, CA equals 0.02 radians. Okay, with respect to and A under MT equals 0.25 ton meter. Calculate the shear modulus of the material. Shear modulus is G, remember, of the material of the cantilever. This is the question B. And the last one here, calculate Pmax and elongation, which is delta CA under Pmax when MT equals 0. Okay, here we have 3 different questions. Okay, let's have a look the first one. Let's have a look the first one. Let me see. Yes, the first one is perform stress check on AB and CB. Okay, when P is 0 and MT is something. P is 0 means here in this question, there is no axial load. There is only torsional moment. Okay, we are gonna only consider the torsional moment at NC, as you can see, which is red on the sketch. Okay, we will do it. Let's have a look at a new page. Sorry. Here. A. Now we know that we are going to do this under only torsional effect. We can draw the torsional diagram. Okay, we can draw the torsional diagram. It's easy. Remember, when we have a moment like this red one, what we do, we use the right hand rule. Our 4 fingers follows the moment direction. Okay, and thumb shows us the moment vector direction. If we do that like this, our thumb goes to right hand side. So it's gonna be like here. This is the cantilever, you know. We convert the MT to a vector like this. This is the MT. So after we convert the torsional moment to a vector, moment vector, we can draw we can assume this as a axial force, and then we can draw the axial force diagram that gives us a completely torsional moment diagram here. So let's do it. Okay, we have the moment vector. Now let's draw the axial force diagram for this vector. So we will see this one. Let me see. So it's totally constant all along the cantilever and positive. So it will be like this. MT means here 0.25. 0.25. So what this diagram says us, actually, we see a constant torsional moment all over the cantilever that we are dealing with. So we will use this constant torsion in our calculations. Okay, let's do it. Remember, we have to calculate first the polar moment of inertia. Polar moment of inertia. How we do it? Remember, polar moment of inertia is I0 P times R4 over 2. This is the polar moment of inertia. Okay, I draw this cantilever as the line here, but it has the two portions. Okay, we have a large section here and we have a smaller section. For each part, we are going to calculate this I0. Let's do it. I01, let's say. For the solid section, the diameter is 10 centimeters, so radius is 5 centimeters. P times radius power 4 over 2 equals, let me see the result. Yes, this is I01 for the solid section. For solid section. I02. So I02 is the second portion, and there is only a circular hollow section over there. We are going to calculate the I0 polar moment of inertia of this section. It's easy. We are going to use the same equation here. P over 2 is the constant value. Here the outer radius here is 4 and inner radius is 3. Okay, so from the total solid section, we remove the gap inside the section. So the equation is this. What we are gonna have, let's see, this one is I02 for a circular hollow section. Okay, now what we will do, we will do a stress check. So what kind of stress are we gonna deal with? In question A, what it says, there is only torsional moment, torsional moment. If we have a torsional moment, you know, we will have shear stress on the structural member. Okay, shear stress. We are going to calculate that shear stress here. For the portion 1 to 1 for the solid section. What we have moment here. Moment. This is ton meter. Let's convert it kilogram centimeter to do this. Up. Add this one here. And I0 is what for the section 1? Times R. R is the radius of the section. Is this. So the general equation, let me write the general equation, by the way. Tau is m torsional over I0 times R. Okay, we are following this equation. This is for the portion 1, the solid section. Yes, this stress here is this one, 127. Okay. And so we have to check if this stress less than the allowable stress or not. Allowable stress is given in the question here, to allowable, which is 900. Take a look here. This is less than 900. And this section works for distortion. But we are just talking about the portion 1. Now we're gonna go ahead to tau 2, which is for this portion. This is the portion 1, portion 2. Okay, the circular hello section. The moment is constant all along the cantilever. That's why moment is same. So what is I0? I0 was calculated here. Times radius. Radius here is what? 4, because total diameter here 8, the radius is 4, equals, if you make this calculation, you are gonna have, let me see, and which is also less than 900 kilogram centimeter square. Okay, our section works for this given moment. This is the A. Okay, this is A. Now we will do the question B. Question B, if the rotation of this point is given, okay, under this moment. So the question is, what is the material property, which is shear modulus? Calculate the G. Okay, yes, we can do it. Let's have a new page. New page. This is B. This is B. Theta, the rotation is mt times L over G times I0. This is the general equation, which gives us the rotation under torsional moment. Okay, so we have the total rotation. Our section is this. Okay, we have to consider each portion. This is the portion 1, remember. This is portion 2. And in this all these portions, we have constant torsional moment, right? So we can do it easily now. Let's, for this point, we are gonna write the theta equation, then we are gonna write it for this portion too. The summation of these separate portion rotations gives us the last product, last result, which is for point C. Let's do it. Let's do it. MC theta CA is given 0.02 radians. It equals. We know the torsional moment, which is it's constant. Okay. The 10 power 5 is just for unit conversion times the length of the member is 1 meter, so 100 centimeters over G times I0 that we calculated in the previous page, plus for the second portion, the moment is same times 6 over G is G, which is unknown, and I0. So this is the equation. In this equation, we have only one unknown here. It's easy to calculate one unknown, one equation. If you make this calculation, you will see shear modulus, which is this. Shear modulus of the section. Now we have just calculated the question B. Question B. Now let's do the question C. Calculate the P max and elongation under P max when MT is 0. Let's have a look to sketch again, given in the question. MT is 0. That means there is no torsional moment. There is only axial force, which is tension. Okay, which is tension. So it's easy. Just a second. I'm gonna do one more thing. So under this, well, what's the problem here? No, share screen. Under this axial force, we are gonna calculate maximum one. Let's do it. It's easy. You know, the axial force is proportional with the area. So we have two sections here. The first section is, you know, let's go back, take a look at section. This one, which is a large section. This is a smaller section, you know. So we can calculate a capacity from here, area times sigma allowable, and area times sigma allowable. So we have the capacities for each section. That's okay. But if we are talking about the total capacity of section, the minimum one The minimum one is the capacity of that member. So we have to find the minimum area, because the stress is, you know, the force is stress times area. The minimum area gives us the total capacity of the section. Here for C, let me clear this part. P max is A mean times sigma allowable. Section is like this, remember, right? Okay, this has a capacity. Okay, this portion is a capacity, and this portion has another capacity. But if we are talking about the capacity of total section, total cantilever, the minimum one is the total capacity of section. That's why we are dealing with A mean, because it's directly the maximum force directly proportional with the area. Allowable stress is allowable stress times area. So that's why we consider the minimum area. Let's do it. The area is what? Let me see. If you calculate the hollow section part, you're gonna see this centimeter square times 1.4. So the force is this. Okay. Maximum force is this. So the question is, what is the elongation of the cantilever beam under this P max? Okay, P max, remember the elongation. Elongation equation is this. Axial force times L over EA. So we can write this equation for each part of the member. P is P for each point of the cantilever. This is ton converted to a kilogram. The length of the member, the first portion, 1 meter. So it's 100 centimeter. E is E given in the question. And A, the area here. This one. Plus, this is the portion 1. Let's have a look at portion 2. Axial force, yes, axial force. Times length is 0.6 meter, 60 centimeter. Elasticity modulus is same. The material is same because so the area is this. So for each portion, solid and the hollow section parts, we write this equation, the elongation equation, and then if we calculate this, delta CA 0.059 centimeter. This is the result. Okay. In one question here, we asked the torsional moment, subject, and also axial force here. That's why it's easy to calculate. I believe in that you can do it easily. Any questions so far? No. Okay, let's solve another question. Let me see what we have, by the way. We have different question, but we can do it this one. Another question is about the moment and combined axial force case. We have a we have a beam, simple beam actually, pin support, roller support. At the midpoint, we have a force like this. This is P1. This is P2. Okay, the length of the member here, 5 meter, 5 meter. Okay. Question here is calculate the maximum and minimum axial stresses, all normal stresses, under M plus N case when P1 equals 6 tons and P2 equals 25 tons. Okay. We by the way, the section of this number is a box section. Like this. All the dimensions are here. Uh, 2, 2, 28. This direction is X. This is the Y. X and Y axis. Here 1 centimeter, 1 centimeter, 18 centimeter. By the way, all the dimensions are in centimeter. Yes. Okay. Also in this question, the allowable stress is given here. In this question, the Ix and Iy is given. Okay. But please try to calculate this moment of inertia by yourself. Okay, here I'm giving the moment of inertia values in this question. But if you know how to calculate this problem, if you can't calculate the moment of inertia correct, you can't solve the problem. Okay, that's why please make a few examples by yourself. It's regarding the statics course. Okay, it's not the subject of our strength of material course. Okay. Now we will do the MRTN stress check. Here, let's have a look at the axial force. Axial force, is it tension or compression for the member? We should decide that, because remember, our stress equation is N over A plus minus M over W, elastic modulus. Okay, so okay, we know the moment part is like this. Why? Because in moment, one side will be in compression, one side will be in tension. That's okay. That's so that's why we use plus and minus here. Okay, but for this part, is it positive or negative? We have to decide it. It's completely about the axial force. If it's tension, it's positive. This is positive. If it's compression, it's negative. Remember, these signs, positive or negative, is completely about the direction of the force or stress. Tension is always positive. In this example, if we draw an axial force diagram, we are gonna see this P2 goes right hand side. Yes, it will be like this. Okay, P2, P2. So this is positive. So here is positive. Now, let's write the equation. Here, the sigma is axial force. Axial force is, 25 tons. Converted centimeter. Okay. No, converts to kilogram. That's better. This is ton. I'm sorry. This is force. And over A, area. You can calculate the area of this box section. It's easy. I assume that you can do it. It's 1/36 centimeter. This part is positive. So here is positive or negative altogether. We have, the Ix and Iy. Which one we are gonna use? We are gonna use the Ix here in this question. Okay, let me write here the moment. By the way, we should draw the moment diagram to see what the moment is here. Let me draw it here. There is an axial force at the midpoint, so the moment diagram will be like this. Please try to calculate the moment diagram by yourself. It's easy. Okay, this value is P. What is P? Over 4. So it's 15 ton meter. Okay, this is the moment diagram. It's positive. Let's write the 15 here, 15 here, 15 ton meter. Convert it kilogram centimeter with 10 power 5 over Ix, which is times y, the distance to the top or bottom end. So totally it's 32 centimeter, right? Yes, 32 centimeter. The half of 32 is 16. Okay. This portion is, let me remind you what this portion is. M over Ix times y. So from here, if you make this calculation, sigma is, we will have two results for the minus side and the plus side, which is this, and the other one is, remember, this minus or plus only regarding the direction of the stress. So we check this stress as an absolute value with the allowable stress. So both stresses are less than allowable stress, and the section works under this loading condition. Okay, under this loading condition. Yes, we have this one. Let's solve another problem. Do I have any different example here? I'm trying to solve with different problems. Most of the problems are same. Let me see my iPad. Maybe I have different examples. Yes. Here we have some examples. T max and max. Okay. Let's have a look at this equation. Yes. This example. Question 3. Here we have simple beam again. Okay, this is the 20 ton meter. The section of the beam is rectangle. Okay, and here this dimension is b, this dimension is 3b. 3b sigma allowable is this tau allowable is if in the question a displacement allowable displacement level is given, it can be checked for that. But if it's not given, just check the or calculate the dimensions according to given allowable stresses. I will show you. E is important. No, it's not important. I'm not gonna. The design the given section according to given loading condition. Okay. What we are gonna do here? What we are going to do? So at the end of the day, we have a beam. We need to know the internal forces. Remember, we should draw the first, or we should calculate the internal forces. After that, we will use all these internal forces in the section design. We have a uniform distributed load. We can draw the shear force and the moment diagrams for this member. Let's change this. Here, this is the shear force there. Now it's going to be like this. Okay. Here, let me clear this up. Yes. Let's calculate the value, the maximum shear or support reaction will occur at the support. So these support reactions is a kind of shear force on the beam. We can do it 0.20 times. By the way, I forgot to give you the length of the beam. I'm sorry. What was the length of the beam? 3 meters. This is important to calculate this one. 3/2. Okay, 3/2. This is the 0.30 ton. Here is 0.30, and also here is 0.30 tons. This is but was too negative. And also, we will have a curve like this. When the shear force goes 0, we're going to have the maximum moment at this portion, the M max. Q 0.2. You can calculate it step by step according to how we draw the internal force diagrams. I'm going to directly write the equation here for the maximum result. Q 3 or this. This gives us the maximum moment for uniform distributed load. Okay, we have shear force and the moment. Okay, when we look these diagrams are important. The maximum shear force and maximum moment, which are not at the same location at the same time. For example, when we have the maximum shear force, as you can see in the first diagram, we have moment 0. Likely, when we have the moment maximum, we have shear force 0. So we know that at the same time, we don't have the maximum internal forces according to these internal force diagrams. Okay, so how we are going to design this section? We will design the section according to the moment. Okay, we will design the section according to moment. We will decide the dimensions. After that, we will check this section for the shear force. That's it. We are make separate calculations for moment and the shear force. Design it for moment, check it for shear force. Okay, let's do it. For moment. Remember the W, which is the section modulus, which is the section modulus. So moment over sigma equals m over W. I am going to do that. The moment is here 0.25 times 10 power 5 over B times 3B square over 6. Okay. Equals allowable stress, which is 120. Okay. Which is 120. Now, this part is completely regarding the W. The 3B here is H. This is H. Okay. There is a relationship in between the width and height of the section. It's proportional with 1 and 3. That's why we write this equation like this. So when we write this equation here, we will have only one unknown here in this equation. So only B. Yes, it's easy to calculate B here. And the result here is almost 5 centimeters. If this is 5 centimeters, if this is 5 centimeters, the H is 3B. That's why this is 15 centimeters. Okay. Okay. Now, these dimensions are coming from the moment. Let's do it for shear force. for shear force, for rectangular sections, what we were doing, the tau was 3/2 V over A for rectangular sections. Here, be careful. This equation only for rectangular sections. If we have any other shapes like box section, I section, you can't use this equation. Okay, this is only for rectangular sections. So shear force over area times 1.5. Allowable stress here is, what was it? Allowable stress given question 12 times 1.5. The shear force was 0.3 tons times 10 power 3. We converted to kilogram, and the area is B times 3B. B times 3B. By the way, we can check this. Instead of to calculate B from here, we can put the B that we calculated shear force here, the moment here, sorry. Let me clear this part. We can write here 5 times 15. Okay, 5 times 15. I need, and by the way, I made something not wrong, but this should be like this. We designed the section according to moment. Here we checked these dimensions for shear force. Let me see. So at the end of the day, the stress calculated for the B equals 5 should be less than 12. Let me calculate it. I don't have the result. Yes, here the result is 6. Okay. So the 6 is here, kilogram centimeter square. So this is less than 12. Our selection B is 5 and H is 3B, 15 centimeter is okay. Okay, ladies and gentlemen, let's have a break. Not too long for today, I guess, the 15 minutes or 20 minutes. We will be here at 10:30. Okay, I will show 1 or 2 examples, then we are going to close the session. Okay, see you. Okay. Actually, I'm gonna solve one more question about the backlink, which was the last subject of our course. Last week we did it, yes. This is a kind of recap for it. Actually, so far we recap almost all main subjects with 3 questions here today. I think this is the last question to close the session today. Let's calculate. Let's do it. By the way, what's the number of the question? It's 3, 4. 4 is 4. Up. 4. The beam is again a simple beam. Here we have a load. We have a box section again, which is the same section that we used in the previous questions. Oop. Let me give all necessary dimensions. Here is the x, here is the y, x, y, all dimensions here. 18 centimeter, 1 centimeter in the vertical direction. Here, 2, 28 centimeter. Okay, 28 centimeter. This is the section of the beam given here. The axial load, let me see. The question is here. This is P. The length of the member is here 10 meters. And determine the maximum allowable compression load. Maximum allowable compression, just P load. Okay, for the system, but we need sigma allowable here. And lambda less equal lambda P sigma critical equals the empiric equation. All these are in kilogram centimeter square. Lambda is greater than lambda P equals 120. Euler's formula is used. The N here for this question, which is factor of safety, is 2. For this question, okay, this is the question. To start our calculation, we have to calculate the minimum moment of inertia. Here, I will give you the both of the moment of inertia for the main axis, Ix and Iy. This is Ix, Iy. Here, Ix is and please make these calculations by yourself. to remember how to calculate moment of inertia. I gave this for you. Okay, now we will calculate the allowable compression load. That's okay. So we need lambda, because we are gonna make comparison with the lambda p, and we're gonna decide which method are we gonna use. Okay. So here, let's have a look to structural system. This is like, I mean, K buckling length coefficient, the length of the member, or LK over I mean. This is easily. What is the LK here? What is K? If we take a look at the structural system and the support conditions of this beam, at each end we have pin support. So it's basically a pin supported member. So it's similar to the Euler's member, which which has two hinges at both ends. So this K here is one. This K is one times 10 meter convert to centimeter, 10 goes to 1000 centimeter over I mean to calculate what we will do, remember I mean is coming from the minimum moment of inertia over A. Okay, over A. So take a look these two moment of inertia. Select the minimum one. Area is area of this section. Okay, here. By the way, I have bad experiences about this area calculation. When I check your papers, actually in previous years when I checked the papers, our friends made this area calculations completely wrong. It's just a multiplication. That's it. That's why please make these calculations correct. If you do it wrong, the question is wrong. Even if you have all these equations, everything on the paper, if you calculate the area wrong, which is really basic, you get the wrong solution. Okay, be careful about that. I mean, I'm gonna write I mean here directly. You can calculate it. What is it in my paper? Yes, it's this. So here the result is 132. So when we go here, it's greater than 20. So Euler's equation is used. Okay, let's write P critical square times E. E is modulus of elasticity. Is it given in the question? No. Let me write here is E is, what was E in this question? Yes. Okay, this should be given in the question with the allowable stress. Okay, P squared times E times I mean over buckling length square. So 1 times 10 square. This is the buckling length. You know, K is the buckling coefficient. So here is the critical load. So here we're gonna have this one. Is this the maximum load? No. If you take a look at the question, there is a factor of safety, N, which is 2. So P allowable is, this is almost, so 80,000 kilogram or 80 tons. Okay. Yes, this is the P allowable. This question format is easy. So we calculate the slenderness, which is lambda. Slenderness directly deal with the LK over I mean. So we calculate it, and according to the slenderness, we decide the calculation method. Depending on the slenderness, we may use the empirical equation. It's possible. So we have to check it, which methods we will use. Then we follow it. That's it. Actually, yes, this is done. I guess that's all for the examples. I guess we covered everything so far with 4 questions. Next week we don't have class, and I guess 25th of June we're gonna have our final exam. I'm reading the midterm exams at the moment. I will share with you when I complete it. I guess next week I will do it. Thank you for your joining our class in this term. I hope you're gonna be successful in the final exam. So take care of yourself. See you in final exam. Bye bye.